So now let's talk a little bit about statistics, and specifically frequentist statistics, which is the paradigm that we're really operating under at the moment. So statistics, generally speaking, is the study of numerical data that is used to infer details of a population based on a sample of that population. This relationship between a population and a sample is a really foundational concept in statistics. The history of statistics goes back deep into the past, but in the modern sense, a lot of this work was conducted from the 17th century towards the present, with some foundational studies and analyses developed by demographers and economists, and even people studying gambling, into the 18th century when we've got some development of probability theory, same in the 19th century with the development of some statistical techniques and methods generally applied to evolutionary biology. But it's really not until the 20th century that we have kind of modern statistics really taking form. And a lot of this has to do with the modern synthesis, this fusion of Darwinian natural selection with Mendelian population genetics, and folks like Fisher, who really developed a lot of key ideas in this time period that have served as the foundation and the basis for frequentist statistics ever since. Ideas like the p-value date back to this time period, and a lot of other common statistical tests that you're familiar with. So statistical inference then is kind of the point of what we're doing. Inference is being able to draw conclusions based on observations of a sample. So it's again this idea that we can study the sample to understand the population from which that sample comes. Statistics is therefore, of course, not actually about the sample. It's about the population, right? If we've got a skeletal assemblage of 15 individuals and we measure the length of their femurs, generally speaking, we're not doing that because we care deeply about the femur length of those specific individuals, right? We're doing that because hopefully this can tell us something about the broader population from which these 15 individuals have come. That we can kind of infer something about a more general phenomenon based on studying this subset of the population. And this is really important, and understanding sampling is really important. And one of the ideas associated with sampling is this concept, the law of large numbers, which you may have heard of or may not. This generally says that as sample size increases, the parameter of interest, whether it be the mean, the median, the mode, standard deviation, whatever, the parameter of interest begins to approach the true parameter value. So as you increase your sample size, it is more likely that whatever it is you're measuring will begin to approximate the parameter of the real population. And this little figure here over on the left, just showing you a silly example of dice rolls, where the theoretical mean of rolling a bunch of dice is 3.5, right? But as you start off with small sample sizes, you can end up with average kind of values, average results that are really not even close to that theoretical mean. But as your sample size increases, you begin to approach that true mean of what the overall kind of theoretical average should be. But you can see that even in this case, it takes sometimes several hundred trials in order to get there. So this is kind of getting at the idea that it is often important to have a sufficiently large sample size in order to say something about a population. And so frequentist statistics, which I've said at a couple points up until now, is this paradigm that a lot of modern statistics at this point is still operating under. It has its roots in the early 20th century with Fisher and those guys. And it's named this because it really emphasizes population-level parameters given the sample parameters. And I'll explain this as I work through this slide. Essentially, we assume in this paradigm that a population has a defined fixed parameter, that there is some true value that we're trying to approach in our measurements of a sample. And if we repeat our observations or our experiments as many times as we can, approaching infinity, the most frequent parameter estimate that we get is going to begin to approach that true parameter value. And this is where frequentist comes from in frequentist statistics. It comes from the frequency of the estimates. Whenever we're approaching infinity in our sampling, in our experiments, in our observations, that as we approach infinity, we're beginning to approach that real value that exists out there. And a really common way to engage in this kind of process of statistical analysis in frequentist statistics is called hypothesis testing. Essentially, in this approach, we are trying to discuss or evaluate statistical difference or change or effects that are framed in terms of alternate hypotheses. So this is where the idea of a null hypothesis comes in that many of you might have heard of. The null hypothesis is generally that there is no effect, that there is no relationship or that there is no change other than randomness between a set of conditions, right? So if we look at this image on the left here, we've got a black probability distribution and a blue one superimposed on each other. The null hypothesis is that the values expressed in these probability distributions do not differ from each other. Right? That's the null hypothesis. That any variation we see between the black line and the blue line is just due to random chance, to stochasticity. That it's not really an effect of these two different groups being separate, it's just random chance, it's randomness. Now, the alternative hypothesis, the alternate hypothesis, is that there is an effect that is not just caused by randomness, right? That there's some relationship, there's some change between these two groups in this case. We're now in the bottom of that figure, the black probability distribution and the blue distribution are a little bit different from each other. What we're trying to evaluate here is whether that is likely to occur if the null hypothesis were true, right? If there actually is no effect, how likely is it that those black and those blue lines should look like that? Right? I'll explain this more as we progress, but basically the goal of this whole process is to just assess the probability of the null hypothesis. If we can determine that the null hypothesis is, if our data aren't likely to have occurred if that null hypothesis were true, then we can conceivably reject the null hypothesis and begin to explore these alternatives. So a really important way that we approach these issues is through the use of p-values. Many of you have probably heard of p-values, but I would probably say that most of you don't actually know what they are, unless you've taken a couple statistics courses. It's a very commonly misunderstood statistic, and if I were to ask those of you watching this lecture right now to define a p-value, I suspect that a lot of you might say something about it's maybe the probability of an effect occurring. Perhaps it's the likelihood that two values are the same. Perhaps it's the probability that the null hypothesis is true. These are all some common definitions that are given for p-values, and they're all wrong. The p-value is none of these things. What a p-value is the probability of obtaining your data, or more extreme data, if the null hypothesis were true, and your observations were repeated an infinite number of times. Now that's a very long and kind of very complex definition, but we can break it down, right? A p-value is a probability, first of all. It's not just some arbitrary number, it's a probability. It's an expression of kind of the likelihood of something occurring. And it is, as I said, it's not the probability of an effect or the probability of the null hypothesis. It's the probability of your data, right? And importantly as well, a p-value is not just the probability of your data, but it's also the probability of your data or more extreme versions of your data, versions that are even further removed from kind of the null expectation. So the probability of these data, or more extreme versions, if the null hypothesis were true. This is an important part of the definition. We're assuming that the null hypothesis is true. We're taking that as a given. The null hypothesis is true. What then is the probability that we would get our data or more extreme data? And finally, the key part of this also is if our observations were repeated an infinite number of times. And that's getting at this idea in frequentist statistics that we're sampling a huge amount, repeating our analyses a bunch of times, and as we do that, the most frequent parameter estimate is approaching the true population one. This little mathematical statement at the bottom here is really the definition of a p-value in a simplified form. It's PR stands for the probability, Y stands for your data, and theta stands for a parameter or a hypothesis, in this case the null hypothesis. So what this mathematical statement is saying is the probability of your data, Y, given, the vertical bar means given, given the null hypothesis. The probability of your data given the null hypothesis. That's a p-value, right? That's what we're trying to get at when we calculate p-values. It's the probability that we would get our data if the null hypothesis were true. And I'm going to work through a little graphic example to hopefully explain and clarify this. Let's say that this probability distribution here, this nice normal distribution centered on 0, this is kind of the expression of the population, that there is a true value here at 0, and we're trying to approximate that mean value. If we sample from this population and we get these red data, they seem to fit that probability distribution pretty well. If we sample, again, a second group and we get these blue data, they also seem to fit that probability distribution pretty well. The null hypothesis in this case is that the red data and the blue data both come from the same distribution. Right? That these data are originating in the same way, and that there's no real difference between them. Right? There's no effect of being blue or being red. That's the null hypothesis here. And so a p-value, in this sense, is an expression of the probability that we would get these data if that null hypothesis were true. Right? If there's no difference between being red and being blue, what's the probability that these data would occur? The p-value in this case is really high. This p-value is going to be something like 0.8, 0.9, or perhaps even higher. Because, again, these are simulated data that I created, and they are coming from the same distribution. So the probability that that null hypothesis is true is very high. This is going to be a high p-value. In contrast, if we got blue data that looked like this, way off to the positive side of the red data, as I said, our null hypothesis is that the blue and the red data are coming from the same distribution, that there's no effect of being blue versus red. But in this case, it looks like there is an effect of being blue. It's very different from the red. It doesn't seem like these have come from the same distribution. The p-value in this case is really small. In this case, it's actually a really, really small p-value, 0.0001 or something like that, because it is very unlikely that you would get these data if the null hypothesis were true. These data that look like this are not likely to occur if there's no difference between red and blue. That's what a p-value is expressing, the probability of getting your data assuming that null hypothesis were true. And when we're talking about p-values, this is what allows us to discuss the concept of statistical significance. The idea that something is significant if it is unlikely to occur given the null hypothesis. And the way we decide what is likely or not, or acceptably unlikely or not, is based on this idea of an alpha value. And we generally set the alpha value at 0.05. So if your p-value is greater than 0.05, it is not significant, and if it is less than 0.05, it is considered significant. There are different alpha values that different disciplines will use, but 0.05 is the most common one. But really, it's important to also remember that this is an arbitrary cutoff point. This was decided upon 100 years ago by people like Fisher and others in the early 1900s, who decided that a 5% chance was sufficiently unlikely that we could consider that a significant effect. But of course, it's, as I said, important to realize that this is an arbitrarily chosen threshold, and that a p-value of 0.06 and a p-value of 0.04, even though the former is not significant and the latter is significant, what really is the difference between a 4% chance and a 6% chance? Not much. And so it's really vital that you understand that p-values are useful, but you shouldn't view this as a hard-line cutoff, where if it's 0.051, it is not significant, there is no effect, and if it's 0.049, it is significant and there's a real effect. That's a silly way to understand p-values. If you keep in mind that this is just a probability of getting your data, assuming that null hypothesis were true, it allows you to kind of better comprehend what exactly this p-value is saying. And it's this kind of arbitrariness and some other issues that have caused a lot of problems with the use of p-values over the years. There's been a lot of criticism of p-values from statisticians and scientists, some to the point where they've entirely abandoned the use of p-values. There's some theoretical arguments to be made for this, some conceptual issues, and also some practical issues. And this is why a lot of folks nowadays are turning to Bayesian statistics, which you may have heard of. It's kind of a different paradigm from the frequentist statistics approach that we're using here. And it allows you to avoid calculating p-values entirely. It has a different understanding of kind of what the goal of statistics is that is beyond the scope of this course. But it is becoming more and more popular, and it's something that you will encounter, most likely in the fields of archaeology and anthropology into the future. Another big problem with p-values is this idea of p-hacking, and this is kind of one of the practical issues that people have with the concept. Whenever you've got your data set, a lot of times what people do across all different disciplines is engage in data dredging or data mining, where you run a bunch of different statistical tests on your data, searching for a statistically significant result. This is problematic, and this is problematic for a number of reasons, but we'll discuss the main one a little bit later on in one of our video tutorials. But in essence, a p-value, right, is a probability. If you've got a p-value of 0.04, that's a 4% chance that you would get these data if the null hypothesis were true. That means that there's a 4% chance that you would get these data if there's not actually anything real going on here. And we deem that to be unlikely, and we deem it to be kind of acceptably unlikely that we can consider it a significant result. But it is still possible that you could get data that look like there's an effect going on when there really isn't, and it's just randomness. And that's what the p-value is also expressing. It's the probability of that happening, kind of a false positive in a sense. And so when you run a bunch of statistical tests, dozens and dozens and dozens of them, maybe even scores or hundreds of them, it becomes more and more likely that you're going to find a false positive in there. And if you then report that as a real effect in a publication, it can lead to crises in your scientific field. There's a lot of scientific fields out there. Psychology is one of the highest profile ones, where this problem has come back to bite them in a big way. There are a lot of studies out there that cannot be reproduced because it seems like they were false positives, kind of spurious conclusions drawn from some sort of data dredging or p-hacking issue going on. And so this kind of whole process destroys the meaning of the p-value and renders your conclusions meaningless. So it's really important to understand that you shouldn't be doing this. You shouldn't just be going and searching for any significant result you can find. Start off and operate deductively. Think about a hypothesis ahead of time. Test that. And if it's not significant, you can still report on that. That's important to do as well. Confidence intervals are another important concept kind of associated with p-values. A confidence interval is a reflection of sort of a probability that this interval will contain the true value that you're trying to get at. Confidence intervals are generally set at 95% to conform to alpha values of 0.05, kind of the inverse of that in a way. But of course you can set confidence intervals to any kind of probability in that sense. And similar to a p-value, right, the definition of a confidence interval is that 95% of the time, this specific interval, this specific range of values will contain the true parameter. It's the probability of your data given a parameter, or given a hypothesis, right? Same as a p-value. What a confidence interval is not is a chance that the true population value occurs within that interval. That would be the probability of the parameter, assuming your data were true, and that's not what we're doing in frequentist statistics. That's what Bayesians are doing. We're not doing that. We're discussing the probability of data, not the probability of parameters or hypotheses. We assume the parameter is true. We assume the hypothesis is true. We assume that this interval exists. We're trying to get at kind of the likelihood of this specific interval containing that true parameter. And now when it comes time to report test results, we're going to get some practical experience with this, but I do just want to point out up front that when you're reporting significant p-values, the conventional intervals at which you do this are generally 0.05, 0.01, 0.001, and 0.0001. Whatever kind of threshold your p-value is lower than, report it at the level of kind of the one that it falls under. If you've got a p-value of 0.04, you say that your p-value is less than 0.05. That's the standard in most styles. If you've got a non-significant p-value, if it's larger than 0.05, you actually just report the p-value directly. So if you've got a p-value of 0.06, you just say p equals 0.06. If it's 0.57, you say p equals 0.57. Non-significant p-values get reported directly. And we'll get more experience with this as we work through the examples in this module. And real quickly, I do want to touch on this idea of what to report when you're running statistical tests in terms of the test statistics and degrees of freedom. Now, these are somewhat complex issues that we'll get into more a little bit later on, but in essence, you want to report several other values in association with a p-value. You can't just report a p-value. That's not sufficient. We want to know more about how you got that p-value, and that's why we need what are called test statistics and degrees of freedom. Don't worry about this too much at the moment. We'll get into this a little bit later on, but I do just want to explain quickly what a degree of freedom means, because this is an issue that kind of crops up quite commonly, and you don't need to fully grasp it, I would say, but having a bit of a knowledge about it is important. So a degree of freedom refers to the number of elements or values that are free to vary. Generally, this is your sample size minus 1. Or when you're running a statistical model, sometimes it's your sample size minus the number of parameters that are in your model. That's a bit confusing, so let me explain it with a very simple analogy. Let's say that you flip a coin 4 different times. In this case, the degrees of freedom is 3. It's n minus 1, your sample size minus 1. And let me work through why this is the case. If we flip a coin 4 times, let's say we get 2 heads and 2 tails. If I'm looking at that first coin flip, it could be heads or tails, right? I know I'm going to end up with 2 heads and 2 tails and 4 coin flips. So that first one could be heads, it could be tails. It won't really impact the end result here. That first coin flip is free to vary. It's a degree of freedom. If we get heads on that one, we can then move to the second one. Let's flip that coin. It's also free to vary. We could get heads again, we could get tails. It doesn't really matter because we know that we get 2 heads and 2 tails in the end. So that second flip is also free to vary. The third coin flip, once again, free to vary. We've already got 1 head and 1 tails. We know that in the end we get 2 heads and 2 tails. So that third coin flip could be either heads or tails. Could go either way. It's free to vary. If we get heads on that third one, now we've got 2 heads and 1 tails. So we actually know that that fourth coin flip has to be tails, right? Because we know we get 2 and 2 in the end. So that fourth coin flip is not free to vary. It has to come up tails. This is kind of a simple case of understanding degrees of freedom, but this is the kind of thing that you would need to report when you run a statistical test. You'll see this as we get into it, that when you run a test, you get a p-value, there are other values associated with it. At the very minimum, you're going to have to report the test statistic and the degrees of freedom. In a t-test, for example, which we'll talk about soon, you report the t value, and you report the degrees of freedom. And it's this t value and the associated degrees of freedom that is what permits you, or really permits R, to calculate your p-value. So that's why you need to report those things as well. That's how you get a p-value in these statistical tests. If this wasn't clear, don't worry about it. We'll get into this. Just know that you need to report more things than just a p-value. But we'll discuss all of this in greater detail as we start working through some examples, start actually programming in R, and start running some statistical tests.